Hello and welcome. In this video, we're going to take a look at the definition of the limit of a function, and we'll take a look at some graphical examples to try to help explain that definition. In a future video, we may be looking at a little more precise definition of the limit of a function, so this will give you a pretty good idea about what a limit really means and how to interpret it. So let's start off with the definition here. We're going to start off with a function f of x that is defined for values of x near the value a. And that alone might be a little bit confusing, near the value a. This means that this function includes values around a in the domain, even if x equals a is not in the domain of the function. And we're going to denote this expression, the limit of f of x as x approaches a, is going to be denoted with this notation. Now, when we say that this limit has a value L, in other words, the limit of f of x as x approaches a equals L, this means that the value of the function can be made as close to the value L as we desire by restricting x sufficiently close to a on either side, but not equal to a. Okay, so we can get, essentially, if you want to think about the y value, f of x, we can make that as close to L as we want by simply choosing x sufficiently close to a on either side. But we're never going to have x equal to a. So let's just see if we can kind of come up with an example graphically about finding the limit of a function as x approaches a. Okay, here I've got an example of a function y equals f of x. And let's see if we can find the limit of f of x as x approaches 1, just graphically, to get a better sense of what this means. The function is defined for values that are just slightly less than 1, and just slightly greater than 1. So we would say that this function is defined for values of x near 1. What we're going to do is we're going to pick values of x that are fairly close to 1. Maybe we could start with something like 0.5. Maybe something like 1.5, and then we're going to let these values of x slowly approach x equals 1. If we're picking a value just slightly less or slightly greater than 1, we can see where those points are on the graph. And as we try to get closer and closer to 1, we can see what happens to the y-coordinates. Maybe I'll zoom in here a little bit. And you can see that as I approach from the left, the y-coordinates look like they're going to be increasing. If I approach from the right, it looks like the y-coordinates are going to be decreasing. And it seems that no matter which side I come from, the y-coordinates are going to slowly start converging in on some value, in this case 2. And so we can get as close to 2 as we want. And that's the idea of the limit, is that as we approach from the left or from the right, we can make the value of f of x as close as we wish, arbitrarily close to 2. And all we have to do is just choose x values within a certain range of the value 1. Now, I've got a very similar example here with a function g of x, and the only thing I've changed is I've taken that point that was on the graph and I've removed it. So a little note about g of x equals 1 is not in the domain anymore. Now for us, that doesn't stop us from looking at the value of the limit of g of x as x approaches 1, because we can still look at values of x slightly less and slightly more, and all of those are still in the domain of g. So once again, same process. We can start with a value of maybe a half or 1.5 and start getting closer and closer to 1. Zooming in, that would give us a point just below or above that empty point. And taking a look at the y-coordinates, coming from the left, they'd be increasing and getting closer to 2. And coming from the right, heading towards the left-hand side as x approaches 1, these y-coordinates seem like they would be decreasing. And the y-coordinates would slowly be converging on the coordinate y equals 2 here. So once again, the limit of g of x as x approaches 1 is 2. And it makes no difference whether this point is in the domain or not in the domain, because we're really just saying that we can make the y-coordinates arbitrarily close to 2 without having to be actually getting to equal to 2. And one more scenario where I've taken g of x and I've put a point back, but I haven't put the point back where you'd think I should. I put the point way down here at some coordinates, maybe 1, -2. So there is in fact a point down here. And a little note, I actually wanted to plug 1 into the function, h of 1, I get the y coordinate -2. That is fairly irrelevant though when we're talking about limits. With limits, we're still going to be starting at values on either side of 1 and trying to converge on x equals 1. And zooming in, you can almost imagine that you're a little ant without any care in the world. You're just traveling on this curve. And you see, when I zoom in far enough, I have no concept that there's a point way down there. To you, as this little ant traveling in from the left-hand side, you just see that you're going up a hill. You're going up a hill, and it looks like by the time you get to an x equals 1, it looks like you're going to get to a y equals 2. And if you're this ant traveling from above and you're heading down the slope, still traveling towards x equals 1, then it looks like your y coordinates are decreasing, and it still seems like you should be getting to a y coordinate of 2 when you arrive at your destination. Neither of these ants have any concept that there's this massive hole in the floor and they're about to plummet down to this dot down here. We don't necessarily know that in advance. We just look at the limit. What's going to happen as we get closer to 1? It sure looks like we're going to hit 2, and we can get arbitrarily close to 2. And so, by definition of a limit, the limit of h of x as x approaches 1 is equal to 2. Now, there are some circumstances where the limit of a function as x approaches a value actually might not exist. And here's a very common example of a limit that doesn't exist. Okay, in this example, we've got a function capital H of t, and it's a piecewise function. This time I've actually given it a definition. H of t is equal to 0 for any negative value of t, and h of t is equal to 1 if t is greater than or equal to 0. And so appropriately, we've got an open dot and we've got a filled in dot. Now, what are we going to get when we actually look at h of t and take the limit as t approaches 0? Well, this function is defined for values slightly less than 0 and slightly greater than 0. So we can take a look at the limit from both sides, take a value maybe a little bit less than 0 and a little bit greater than 0 and start getting closer, this time along the t-axis. So if we zoom in a little bit and we pretend that we're on this left-hand side, well, if we pick a value that's a little bit less than 0, we'll end up with a point right here on the t-axis. And as we start approaching to the right, what's going to happen to the y value? Well, this particular value here will have a y coordinate of 0. And as we get closer and closer, it doesn't look like anything's happening to our y coordinates. They seem to remain constant at 0. So from the left-hand side, it looks like we are going to get to our destination here at the open circle. So the y coordinates suggest that our limit should equal 0. Now, if you're on the right-hand side and you're traveling left, well, then you'll be at the value 1. And what's going to be happening to your y coordinates as you slowly start to converge in at the y-axis? As we get closer to t equals 0, it looks like our y coordinates are always going to be equal to 1. And so it looks like we're converging on an overall y coordinate of 1. But unfortunately, these two things don't seem to agree. There is no middle ground where it seems like we can get arbitrarily close to a value from both sides. And that is when we start running into problems with the way that we define this limit. We're supposed to be able to get arbitrarily close to some value, L, for x sufficiently close to a on either side. And that's just not going to happen. We can't get close enough to 1 coming from the left, and we can't get close enough to 0 if we come from the right. So in this case, the limit does not exist. And so we may also decide to just say d and e and maybe drop the equal sign. It doesn't really equal a value. I hope that gives you a little bit of a way to interpret limits graphically. And when we get to this concept of one side having one potential value and one side having maybe another potential value without agreeing, then we can take a look at one-sided limits. And we'll save that for a future video, and we may look at the precise definition in terms of a little bit more complicated argument in a future video. But I will thank you for watching and see you again soon, hopefully.